Hello and welcome to the Kettering Aerospace and Rocketry organization's first ever YouTube video. This video is made especially for the Argonia Cup rocketry competition, but we hope other students and rocketeers interested in KARO enjoy this video as well. In this video, we will be introducing what KARO is, who our members are, and what our 2022 rocket project is. KARO is a rocketry club affiliated with Kettering University in Flint, Michigan, formerly known as the General Motors Institute, or GMI. While classically an automotive school, some students sought to branch their engineering expertise into aerospace as well. Therefore, KARO was founded in 2019, and the organization started with building and launching model rockets such as Estes High Flyers, and eventually worked up to high power, where several students obtained level 1 and 2 certifications. Argonia is going to be the first collegiate rocket competition we've been to, and though we may have less experience than some teams, we are still very excited to launch at Argonia, as well as meet lots of new people who are also interested in aerospace and rocketry. So with that, let's meet our team members.
I'm Salvatore Messina. I'm a mechanical engineer, and I've been on the team since the fall of 2019.
Hello, I'm Jacob Lecluse. I've been on KARO for 3 years now. I am a junior mechanical engineer.
My name is Eric Rollins. I'm a sophomore here at Kettering University, and this is my very first term on the KARO team.
Hi, I'm Jenny Barnes. I'm a senior mechanical engineering student at Kettering University. I'm also the vice president of KARO, and I have been since its inception in the fall of 2019.
Say hi, Hello, my name is Cecilia Link and I'm a mechanical engineering senior at Kettering University. I founded the Kettering Aerospace and Rocketry organization, or KARO, back in 2019 and have been the president since then. I started KARO because Kettering is a very automotive focused school, and I wanted students who were interested in aerospace to have a sort of outlet to where they could explore aerospace and learn more about aerospace components such as rockets. It's been pretty successful so far. COVID-19 slowed us down a little bit, but we've done really well in the past year with exploring high-powered rocketry, and we look forward to competing at the Argonia Cup.
I'm Tim Stiles, a physics professor at Kettering University and the faculty advisor for the Kettering Aerospace and Rocketry organization. I've been involved in rockets for a long time. I have had a lot of fun the past few years working with the students in the group to build and launch rockets, and I look forward to seeing their competition at the Argonia Cup.
Here we have a representative diagram of our rocket, which was modeled using Open Rocket software. At the front of our rocket, beneath the nose cone, you can see where we have our ballast, GPS, and golf ball payload mounted to our top bulkhead. For our ballast, we're using multiple steel plates of varying weights with through holes so they can be slid onto a threaded rod, and thus making it easier to add or remove the plates. Using plates of various weights also makes it easier for us to adjust our weighting as necessary. For our golf ball payload, our team designed and 3D printed an enclosure that could be mounted onto the top ballast plate and thus keep the golf ball secured during flight. You can also see that behind the top bulkhead containing our ballast and other components, we have our main parachute and shock cord. At the other end of the rocket, in front of the engine mount, you can see we have our drogue parachute and shock cord. Connecting the two together is our electronics bay, which holds our altimeters, the batteries to power them, and our deployment charges. Additionally, all sections of the rocket are connected together using shear pins to prevent anything from accidentally coming apart during flight. Here you can see some images of the kit and parachutes we chose for our project. We chose the Intimidator 5 from Wildman Rocketry because it was a highly recommended dual deployment standard rocket that also fell within our price range. It is a 5-inch diameter fiberglass Econoline series rocket that is almost 10 feet tall and is about 13 pounds, not including our customized payload and ballast. We are also using the Recon Recovery drogue and main parachutes that we bought off Wildman Rocketry as well. For our engine, we chose the L400 White Lightning plugged reload motor. It's 98 millimeters in diameter with a 12.24 second burn time, an average thrust of 379.15 newton seconds, and a total impulse of 4,641.58 newton seconds. We primarily chose this engine because it was one of the few available online that would make our rocket reach the 8,000 foot requirement set by Argonia Cup. Here you can see some of the simulations that we ran in the Open Rocket software. The top one is our vertical distance versus time graph, and there you can see our max altitude is around 8,300 feet, which meets the Argonia Cup's requirement of being 8,000 feet or above. Below that is our stability versus time graph, where the red line is our stability margin caliber. You can see where our stability starts at 1.5 and at engine burnout is around 3.3. Upon liftoff, it's recommended that your stability margins be between 1 and 2, so our value of 1.5 puts us at a good point where our rocket should be stable upon liftoff. For our electronics, we are using the MissileWorks RRC2 Plus barometric dual deployment altimeters, as well as the EggFinder GPS transmitter and receiver kits. We chose the RRC2 Plus altimeter because it's a relatively inexpensive altimeter and it is also very easy to install and operate. We chose the EggTimer GPS because it was recommended to us by our friends at the University of Michigan for being relatively low cost and easy to interface with both laptop and phone softwares.